This is the homework for 10, 26, 28a and b, 29ab and c, and 30ab and c. For 1026, you need to find the area of the base of each cylinder below and then calculate the volume of each cylinder. So to find the area of a circle is area equals pi r squared, or I remember by saying apple pies are squared. So if you remember that phrase, apple pies are squared, it should help you remember the area of a circle. So now r represents the radius, and the radius is 5. So we have pi times 5 squared. 5 squared is 25. So we have area equals 25 pi centimeters squared. Now remember, a circle is a two-dimensional shape, so it's squared. Three-dimensional would be cubed. So we have 25 pi centimeters squared. For the approximate value, if you multiply it by 3.14, you get 78 and 54/100 centimeters squared. Now to find the volume of the cylinder, the volume is V equals pi r squared times the height. Well, pi r squared, that should sound familiar because that is the formula for the area of a circle. Well, this portion right here, pi r squared, that's this area. And now we're going to multiply it by the height. So you have that circle multiplied by the height. So base times height. So we have radius squared, which was 5 squared, multiplied by the height, which is given here. The height is 10. So 5 squared is 25. So pi multiplied by 25 multiplied by 10, 25 multiplied by 10 equals 250. So the volume equals 250 pi cubic centimeters. And the reason why it's cubed and not squared is because the volume of a cylinder is a three-dimensional shape, so it's cubic. And to approximate it, if we multiply 250 and use 3.14 for pi, 3.14 multiplied by 250 equals 785 and 4/10 cubic centimeters. For part B, we do the same thing as the previous problem. We need to first find the area of the circle. So remember, apple pies are squared. Area equals pi r squared. We know the radius. The radius is given as 3 4/10. So it's 3 4/10 squared. When we square 3 4/10, we get 11 56/100. So the area, this part right here, this blue part, is 11 56/100 pi centimeters squared. This is the actual value. It's not the approximate value. So if we were to approximate it, we use 3.14 for the value of pi, and you would just multiply 11 multiplied by 56/100 by 3.14. Now to the second part of it is we need to find the volume. And remember, volume equals pi r squared multiplied by the height. One saying that you can use to try to remember this is veggie pies are square and high. So veggie pie, before it was apple pie, apple pies, A for apple, well, V for volume. So veggie pies are square and high. So H now is going to represent the height of the figure. So here, this is going to be our height and our radius. And we've already, again, pi r squared, that's the area of this, and now we're going to multiply it by the height. So we have 11 56/100 pi. Well, that's what we got for pi r squared. We got that over here. So I plug that in, multiplied by the height. The height is going to be 9. So we have 11/5600ths multiplied by the height multiplied by pi. And we get 104 400ths pi cubic centimeters. And again, this is a three-dimensional shape, so it's cubic, not squared. Area, flat surface, is going to be squared. To find the approximate value, 104 400ths multiplied by 3.14 gives us 326 7/10 cubic centimeters. For 1028, we need to find the missing length of this right triangle. In order to find a missing length of a right triangle, we use the Pythagorean theorem, a squared plus b squared equals c squared. Here's the right angle, and I always like to put an arrow pointing towards the hypotenuse, the longest side, which is c. So now I can do a squared plus b squared equals c squared. So 5 squared plus x squared equals 13 squared. The hypotenuse will always be what it equals. So 5 squared equals 25. X squared is x squared. 13 squared is 169. We're trying to find the value of x. That's the hypotenuse. So inverse property of addition is subtraction. We subtract 25 from both sides. 0 pair. 169 minus 25 is 144. So now we have x squared. The inverse property of squaring is taking the square root. Those cancel each other out. They're inverse properties. What you do to one side, you do to the other. The square root of 144 equals 12. The second part was asking, is it rational or irrational? So rational number is anything that can be written as a ratio. 12 can be written as a ratio. If it terminates or repeats, it's also rational. Any perfect square is going to be rational. Square root of 144 is 12. Square root of 25 is 5. Those are perfect squares. Those will also be rational. For 28b, we need to find the missing length. This time, the hypotenuse is the missing length. And this right angle is pointing towards the hypotenuse. So we have a squared plus b squared equals c squared, the formula for Pythagorean theorem. So 3 squared plus 6 squared equals x squared. 3 squared is 9. 6 squared is 36. 9 plus 36 is 45. Now, we don't want to know what x squared equals, so we take the inverse property of squaring, which is the square root. Those cancel out, inverse properties. What you do to one side, you do to the other. And so now we have square root of 45 equals x, or x equals the square root of 45. This is an irrational number. The reason why it's irrational is because it's not a perfect square. Remember, perfect squares are the square root of 100 is 10, because 10 multiplied by 10 equals 100. There's no number that you can multiply by itself to get 45. So it's irrational. It'll go on forever without repeating or terminating. The approximate value is x equals approximately 6 71/100. For 29a, we have 5 to the 3rd power divided by 5 to the 9th power. One way to solve this is that you subtract the exponents if the bases are the same. So you keep the base is 5, and 3, and I remind myself that I use this fraction bar to remind me subtraction. 3 minus 9 equals -6. And then you take the inverse, the reciprocal of -6, which brings it down to the denominator, which is 5 to the 6th power. And if the exponent's 4 or greater, 4 or less, you would simplify it, but if it's 5 or more, typically you leave it in exponent form. An alternate way of solving this is to expand each of these. 5 to the 3rd power is 5 times 5 times 5, and 5 to the 9th power is 5 times 5, 9 times. Now I put multiplying 1 here, and you'll see in a moment why. But it doesn't change the value, because it's the identity property of multiplication. When you multiply by 1, it's just itself. 5 multiplied by 1 is still 5. It's not changing the value. Here is 5 divided by 5, which is 1. This is a big 1. Another big 1. Another big 1. And so I can't have nothing up here. I need a value up here. So I put 1 there. And then I'm left with 1, 2, 3, 4, 5, 6. 5 to the 6th in the denominator, and 1 as a numerator. For problem 29b, we need to simplify ab to the 4th and ab to the 3rd. So it's important to recognize that this one has parentheses. So in the numerator, this 4 is going to the a and the b. It's everything inside. It's a group. So I have 4 groups of a times b. This exponent 3 is only attached to the b. It only applies to the b, not to the a. So for the numerator, think of it as 4 groups of a. ab times ab times ab times ab. In the denominator, we have an a, and b to the 3rd is b times b times b. So what I can do here now is I can create big ones. A divided by a is 1. So that's a 1. B divided by b, 1, 1, 1. Those are all big ones. So those cancel out. And I'm left with a times a, which is a to the 3rd, and multiplied by b, it's b to the 1st. Another way to solve this is to distribute this exponent to both a and b. And I put a to the 1st and b to the 1st. And I distribute this. And remember, a power to a power, you multiply. So a to the 1st multiplied by 4 is a to the 4th. b to the 1st to the 4th, 1 times 4 is 4. And then I have a to the 1st on the bottom. And now we're just dividing fractions with the same base, like bases. A to the 4th minus a to the 1st gives us a to the 3rd. A to the 4th minus, b to the 4th minus b to the 3rd gives us b to the 1st, or just b.